lecture in the lecture course of Tony Yu, and the title. By the way, we put your slides you sent to the webpage of the conference in High School of Economics. I don't know about Miami, so they're available for people. So please start.
Oh, thank you for the introduction. And let me share with you the slides in the chat. Yesterday, I wasn't able to do it because it didn't let me to share files. So I have put it on my website, and you can just download from this link. And thank you very much for coming to the second lecture. In the previous lecture, I explained the Frobenius structure conjecture, and today I will explain an application to the moduli space of Calabi Yau pairs. Recall, we have the following conjecture regarding the moduli space of stable pairs. Any connected component Q of the moduli space of triples X, E, which is a sum of E1 to En, theta, where X is a connected smooth projective complex variety, E in the anticanonical class of X is a normal crossing divisor with a zero stratum, and every piece EI is smooth, and theta in X is an ample divisor not containing any zero stratum of E. And we conjecture that such connected component of moduli space is unirational. So why it's called Calabi Yau pairs, I have explained yesterday. I mentioned many terminologies such as what is a pair, what is a stable pair, what is Calabi Yau pair, what is polarized Calabi Yau pair. And with these notions, we have a more precise form of the conjecture. Because for sufficiently small epsilon, if we take X, if we consider the pair X comma E plus epsilon theta, then our moduli space of triples immerses into the moduli space of stable pairs. So we can take a closure of our moduli space Q in the moduli space of stable pairs, and thus we have a precise form of our conjecture, conjecture for the compactified moduli space, which is Q bar admits a finite cover by a complete toric variety, T. So in this lecture, I will explain how the Frobenius structure conjecture, the idea in the Frobenius structure conjecture can be used to study this conjecture for the moduli space of stable, for the moduli space of Calabi Yau pairs. What we can prove for the moment is that is the following special case. The conjecture holds when X is a Delpetal surface and E is a cycle of -1 curves, and the theta lies in the anticanonical class of X. In order to study the conjecture in more general cases, we will need more machinery from mirror symmetry to work. For the moment, let's first talk about the two-dimensional case, the case of Delpetal surfaces. The proof of the theorem is based on the synthetic construction of the family of triples X, E, theta over the toric variety T. So our conjecture says that the moduli space Q bar has a cover by a toric variety, and the idea for the proof is to construct this family over the toric variety, which is an extension and a compactification of the affine mirror family we discussed in the last lecture, and which will work at the same level of generality as in the Frobenius structure theorem. So let me first explain the rough idea of how things work. Here is the rough idea for constructing this synthetic mirror family. We start with YD, the mirror Calabi Yau pair. And note that in the Delpetal case, it is self-mirror, meaning that the mirror of Delpetal pair is again it's itself. So that's why the two-dimensional Delpetal case is particularly easy. And in general, we need to apply the mirror construction twice. So we start with YD, mirror Calabi Yau pair, and assume, as in the Frobenius structure theorem, assume the interior U is smooth affine containing a Zariski open torus, D normal crossing, and Y funnel. Let's consider K to Y, the canonical bundle, and K to K bar, the contraction of the zero section. Just a few observations. Since K to Y is a line bundle, we have the identification of the Picard groups. And also we can identify the cone of curves for K over K bar and for Y, because K over K bar, the only thing that's contracted is just the Y. And we can also identify the Neff cones. So first question, what will be the toric variety? Our conjecture says that Q bar admits a cover by a toric variety. What is this toric variety? And the idea is that we construct a complete fan denoted sec of K over K bar supported on this Picard vector space called the secondary fan for the pair YD. This fan that we will construct is a generalization of the Gelfand-Kapranov-Zelevinsky secondary fan for reflexive polytopes. So in the case when YD is toric, the fan I'll explain is isomorphic to the GKZ secondary fan for the associated polytope, and hence we call it secondary fan. And the second, it is by construction a coarsening of the Mori fan for K over K bar. Mori fan is defined using the Mori equivalence relation for divisors. I will explain in a moment. And we conjecture that the toric variety associated to the secondary fan should be the base toric variety for the mirror family of triples XE theta. Recall the affine mirror family spec A to spec R from the Frobenius structure theorem. So in the Frobenius structure theorem, we have in the Frobenius structure theorem, we had an affine mirror family. We had the mirror algebra A, and we take a spec. We have we obtain the affine mirror family, which we denoted by curly V, from spec A to spec R. And note the dual of the cone of curves is the Neff cone, Neff Y. So spec R is the toric variety associated, is just the toric variety associated to the Neff cone of Y. Theorem, the affine mirror family that we constructed in the Frobenius structure theorem compactifies and extends to a family of Calabi Yau pairs, curly X, curly E to the toric variety associated to the secondary fan. And this is a complete toric variety. Moreover, we have an ample divisor, theta in X, such that the generic fiber X, E plus a sufficiently small multiple of theta is a stable pair. So this theorem gives us some control on the singularity of. So first, the theorem says that our affine family compactifies and extends, and furthermore, the theorem gives us some control on the singularity of the mirror family. And we expect the stability to hold in all dimensions, but currently we can only prove for dimension 2. And we need this condition. Recall that for the triple to be, recall that in our definition of polarized Calabi Yau pair, for the triple to be polarized Calabi Yau pair, we need this stability condition. So, but the stability condition, it's very hard in higher dimensions. And in dimension 2, we have much better control on singularities, and we can show much more in dimension 2. For the moment, for higher dimensions, for the stability condition, we only have it for the generic fiber. But in dimension 2, we have more. So assume that Y is a smooth Del-Petro surface. Then the family produced by compactification and extension to the toric variety associated to the secondary fan is a flat family of Calabi Yau pairs. Now, recall from the definition of Calabi Yau pairs, this statement is essentially a statement of singularities. That is, we say that this pair is semi-log canonical and kx plus e is trivial. And the second, concerning this boundary E, it's a trivial family of a cycle of rational curves, just like D, but it's mirror to D. And 3, for every fiber Xe over the structure torus, the torus with co-character lattice, the Picard lattice, inside the toric variety associated to the secondary fan, X is a Del-Petro surface with at worst dual singularities. And E inside X is an anticanonical cycle of -1 curves. We say kx degree -1 because of the presence of these singularities. And the self-intersection number of kx is equal to the number of irreducible components of D. Recall that by definition, the degree of a Del-Petro surface is just the self-intersection number of the canonical class. So over the structure torus, we really get a nice family of Del-Petro surfaces with at worst dual singularities. And then we show that for sufficiently small epsilon, we get a family of stable pairs. If we put the epsilon multiple of theta to E, we get a family of stable pairs. While in all dimensions, we only know for the generic fiber, but in dimension 2, everywhere it's stable. So we can consider the induced map from the base, toric base, associated to the secondary fan to the moduli space of stable pairs, and we show that the induced map is finite, thus providing the conjectured finite cover from a toric variety. And now, how do we So in order to get the conjectured cover from the toric variety, there is one more thing to do. So we have to relate our family that we constructed with the modular space Q in the conjecture. And that's not difficult. It's just it's an easy corollary by some dimension count. So here we consider Y as above a smooth complex Del-Petro surface, and we assume moreover that D in Y is an anticanonical cycle of -1 curves. In this case, the generic fiber of the mirror family is smooth, and the one fiber is just the original YD. So it shows that the mirror construction is, in this case, for Del-Petro surface, it's self-mirror. YD, the mirror of YD, the mirror family of YD contains the original YD. And the image of the finite map from the toric variety associated to the secondary fan to the modular space of stable pairs is just the closure Q bar for the modular space Q of triples X E theta for this original pair YD. So this shows the conjecture in dimension 2. And we have this assumption that D is an anticanonical cycle of -1 curves. Without this assumption, the mirror family, the generic fiber will not be smooth. All the fibers will be singular, and we can have an analogous statement, but it's a bit more technical to state. So that is the rough idea for the application of the Frobenius structure conjecture to the study of modular space of Calabi Yau pairs. And now let me give more details about our generalization of the Gelfand-Kapranov-Zelevinsky secondary fan. So we used this generalization to construct the base for extending the mirror families, but we believe that our generalization of this GKZ secondary fan may also have independent interest. Here is our setup. We have V, a smooth log Calabi Yau, V in K, some normal partial compactification, and we fix a regular proper map Q from K to K bar, and we assume that K over K bar is a relative Mori dream space. I'll explain this notion, Mori dream space, in a moment. This is the general setup. In our application, we have YD mirror funnel, U, the interior log Calabi Yau. We have canonical bundle K over Y, and we take this log Calabi Yau V to be simply K minus Y restricted to U. And we take this regular proper Q to be K to K bar, contracting the zero section of the canonical bundle. Now let me give the definition, give the heuristic idea of a Mori dream space. The precise definition is a bit technical. A Mori dream space X is a projective variety such that the Mori equivalence of line bundles, I will recall the notion of Mori equivalence in a moment, such that the Mori equivalence of line bundles gives rise to a finite polyhedral fan, Mori fan of X, called Mori fan, supported on the effective cone of X inside the Picard vector space. And people are interested in Mori dream space because Mori's minimal model program becomes particularly simple for Mori dream spaces. Now let me explain what is the notion of Mori equivalence for line bundles. For L, any line bundle on the projective variety X, we consider the associated section ring RXL, which is by definition direct sum of sections of tensor powers of L. If the section ring is finitely generated, it gives rise to a birational contraction from X to the proj of the section ring. And we say that two Q-line bundles with finitely generated section rings are called Mori equivalent if they give rise to the same birational contractions, and moreover, if they have the same stable base divisors. We have to include the second condition because the base divisors we are unable to see from the birational contraction. An easy consequence of the idea of Mori dream space is that each maximal cone of the Mori fan is of the following form. We consider birational contraction f from x to x prime, and we take the pullback by f of the nth cone of x prime plus the subcone spanned by f exceptional effective divisors. And that's all maximal cones of the Mori fan are of this form. And it's useful to distinguish one part of the Mori fan. We introduce the following notation. We denote by move fan the restriction of the Mori fan to the moving cone, consisting of moving divisors. A divisor or line bundle is called moving if it has no stable base components. Then, maximal cones of this moving part of the Mori fan, they are always of the form the pullback of nef of x prime for any SQM, which is short for small q factorial modification of f from x to x prime. So the reason is that recall that all maximal cone of Mori fan is of this form, which has a part subcone spanned by f exceptional effective divisors. But note that any exceptional divisor must lie in the stable base locus. So when we consider maximal cones of the moving part, since the line bundle has no stable base components, has no stable base divisors, then this map F, the associated birational contraction F, cannot contract any divisors. Therefore, it is a small birational map or small birational modification. And we ask it to be Q factorial. You can ignore this. It's just some technical condition in the definition of a Mori dream space. So the moving part of the Mori fan, the description is particularly easy. We don't need we only care about these small Q factorial modifications. And other maximal cone, so other maximal cones that are outside, other maximal cones of the Mori fan that are outside the moving part, they are called bogus cones. They are the cones which has the part given by exceptional divisors. We observe that in the toric case, that is, in the case where the pair YD is toric, the Mori-Fan for this K over K bar. So I introduced everything in the absolute situation, and they all work in the relative situation. If we consider the Mori-Fan in this relative Mori dream space, K over K bar, then one can show that this is isomorphic to the classical Gelfand-Kapranov-Zelevinsky secondary fan. Associated, so the classical Gelfand-Kapranov-Zelevinsky construction has nothing to do with Mori geometry, birational geometry, or Braikovich geometry. It's a combinatorial construction. And if we apply it to the polytope associated to the toric variety, we get the same fan as what we explained above using Mori equivalence relations. Then maybe we can try to use this Mori fan as base for our mirror, for the mirror family. But however, in general, the toric variety associated to the Mori fan, since we will be working with K bar all the time, let's just omit K bar from the notation. So in general, this toric variety associated to the Mori fan is not the right base for extending the mirror family. Because if we do like this, then the induced map from the toric variety associated to the Mori fan to the moduli space of stable pairs SP will not be a finite map. So in order to remedy this non-finiteness, non-finite meaning that it's a bit over some subvariety, we have trivial families. So in order to remedy this situation, we would like to contract a strata of this toric variety associated to the Mori fan on which the extended mirror family is trivial. And our idea, the idea is to construct a coarsening of Mori fan using Berkovich geometry. And in this way, we obtain this sec k. We denote the coarsening by sec k. We call it secondary fan. In the toric case, actually, no coarsening is needed. Toric case is particularly simple. No coarsening is needed, and the secondary fan is just the same as the Mori fan. But in general, we have to coarsen this Mori fan in order to produce a finite cover of the moduli space. So for this coarsening, let's consider the universal torsor. We consider the universal torsor G, which is the relative spec of direct sum of line bundles. And note that the restriction of G to V denoted by T is again a log Calabi Yau variety. Then we have a log Calabi Yau variety T mapping to a log Calabi Yau variety V. And this gives a map of essential skeletons between these two log Calabi Yau varieties. Essential skeletons are some polyhedral subset of the analytification of these log Calabi Yaus. And here we need some extra care since we only have some partial compactification. It's not total compactification, and I will explain it in a moment. And this, the universal torsor T, the restriction of the universal torsor T to V, this is a torus bundle, algebraic principal torus bundle. When we take skeletons, we get a affine bundle. And what is good about this affine bundle is that it admits a canonical section phi, and I will explain the construction of this section phi in a moment. And the idea is that we can glue the maximum cones of the moving part of the Mori fan for which the associated phi coincide. So for each maximum cone of the Mori fan, we have an associated section phi. And if two cones, they have the same associated phi, we just glue them together. And it turned out that it makes sense. We can glue them and we get a coarsening of the moving part of the Mori fan. And furthermore, it turned out that this coarsening of the moving part induces also a gluing of the bogus cones. And finally, it induces a coarsening of the total Mori fan, which is by definition the secondary fan, sec of K. So this is the rough idea for our generalization of the GKZ secondary fan. And now let me explain some ingredients inside this construction. First, let me explain the construction of the section phi of this affine bundle from the essential skeleton of T to the essential skeleton of V. Very generally, we consider the following situation. We consider curly X, curly Y, formal schemes locally affine representation over the ring of integers of some non-Archimedean field. And we consider F from curly X to curly Y a flat surjective morphism with geometrically integral fibers. And we consider the map between the generic fibers from X eta to Y eta. And the claim is that in this situation, we always have a canonical section phi. So how do we make this section? Given any point y in the generic fiber of curly Y, we have we consider the complete residual field Hy. And so our goal is to define what is phi of Y. We want to construct a point in curly X eta. So let's consider the complete residual field Hy. And we have curly X over curly Y, and we consider the formal spectrum of the ring of integers of Hy to Y. And we take a pullback, which we denote by curly Z. By construction, the generic fiber of Z is just the fiber over Y of the generic fiber of X. And now let's consider the reduction map for this formal scheme curly Z. So, so for any such formal scheme of locally finite representation, we always have a reduction map from the generic fiber of the formal scheme to the special fiber. And by our assumption, the special fiber is integral. So it has a unique generic point, eta ZS. And by Berkovich theory, if we consider the pre-image by the reduction map of this unique generic point, that pre-image contains only contains exactly one point. So roughly speaking, this point is just given by the derisorial valuation associated to this unique generic point. And we define the value of the section on the point y to be this unique point. So it's very general and abstract, maybe, construction of this canonical section. So now let's apply to the special case where K has a trivial valuation. So we consider X, Y, K varieties, and F from X to Y a flat surjective map with geometrically integral fibers. Then, so in this general situation, we considered generic fiber. And here, in this trivial valuation case, the generic fiber of X is isomorphic to some construction called X bet, which is a subset of the analytification consisting of somehow valuations whose center is contained in X. So we have, in the trivial valuation case, one can construct a subset denoted by bet, and this subset coincides with the generic fiber. And the subset is the whole analytification for proper X. Then we apply our general construction var phi, general construction phi. We obtain a canonical section phi of this map from X bet to Y bet. So that's the construction of phi. And now recall that we want to glue cones of the Mori fan according to their associated phi. So let us compare the sections phi for different SQM. Let's first consider the moving part of the Mori fan, which are given by these birational maps without these small birational maps. There is a small technicality which you can perfectly ignore, is that the Picard group of K may change under a small birational map. So for this, we fix some scaling of the Picard group for sufficiently divisible n such that, like, it no longer changes, such that n times pic k prime is free and lies in pic k prime for any small birational modification, k prime over k. And recall, we have our universal tosser G over K, whose restriction to V, denoted by T, is again a log Calabi Yau variety. So we have a principal torus bundle T to V. If we take the associated essential skeletons, we obtain an affine bundle from the essential skeleton of T to the essential skeleton of V. And in order to make use of our general construction, we intersect with this bet things, bet of G and bet of K, because of non-properness of G and K. And then we can apply our construction of the canonical section phi And by applying this, we obtain a canonical section. We denote the left-hand side by gamma tilde, the right-hand side by gamma, and we obtain a canonical section phi from gamma to gamma tilde by the construction above. So this is what we do for K, for our K. And now given some small birational modification, K prime of K, we have a universal torsor G prime to K prime. We apply the same construction, but using K prime instead of K. We have universal torsor G prime to K prime, and similarly, we have the analog gamma tilde prime and gamma prime. Since the volume forms, they agree, whatever birational modification we make, one can identify gamma with gamma prime and also gamma tilde with gamma tilde prime. These parts of the skeleton, they somehow only see the birational geometry. They don't see any small modifications, but this section phi prime from gamma to gamma tilde may well be a different section from phi. So now we can use this phi to glue cones of the Mori fan to obtain the secondary fan. And we prove that the gluing of maximal cones of the moving part of the Mori fan with given phi give rise to a convex cone. It's not so obvious because what we do is we just glue cones. So we have a fan and we glue cones with the same section phi. And the theorem says that we obtain a convex cone. So this gives the coarsening on the moving part of the Mori fan. And next, let's consider how to also glue the bogus cones. For each bogus cone, the bogus cones are of the form pullback of nef z plus the cone spanned by exceptional divisors, corresponding to some birational contraction. It should be dot birational contraction k to z, and we let gamma b be the minimal cone of the moving part of the secondary fan containing this pullback. This pullback is just the intersection between the bogus cone and the moving cone. If two maximal bogus cones, they have the same gamma b, then we show that they have the same associated exceptional loci. So in other words, if we can glue, in other words, when we glue the maximal cones inside the moving part of the secondary fan, then we can it also induces a gluing of the bogus cones that are attached to the moving cone, because they have the same exceptional loci. So we can just glue them together. There's no conflict. And the consequence of 1 and 2 is that they induces the secondary fan, sec k. They induces a coarsening of the total Mori fan, which we call the secondary fan, and it is a rational polyhedral fan with the same support as the Mori fan, the effective cone of K. So this is the construction of the generalization of the GKZ secondary fan, whose associated toric variety we conjecture to be should be the correct base for the mirror family. And now finally we have to extend mirror families over this secondary fan. We have to glue mirror families over this secondary fan, and I will quickly sketch how to do this. Recall our setup. We have some final variety y and some normal crossing anticanonical divisor containing a zero stratum d. We have the interior log Calabi Yau u, k2y, a canonical bundle of y, and we have another log Calabi Yau v, which is just k minus y restricted to u. And we have the contraction k to k bar of the zero section. This was our setup. The Frobenius structure conjecture implies gives rise to a mirror algebra AY over RY, the monoid ring over this cone of curves. And recall that AY is a free RY module with basis the integer points in the essential skeleton, and we constructed the multiplication product structure on AY by counting non-Archimedean holomorphic disks. So recall that if we take spec, this is mirror algebra. If we take mirror family, spec of mirror algebra. If we take spec, the spec of RY is just the toric variety associated to the Neff cone. And we have identifications between the Picard groups and also identifications between the Neff cones. Our goal is to compactify and extend the affine mirror family spec AY to spec RY, as I said, which is the same as the toric variety associated to the Neff cone. We want to extend the affine mirror family over this complete toric variety, the toric variety associated to the secondary fan. So let me sketch how the extension works. In the first step, we consider the mirror family for any small birational modification k alpha of k. By our setup, we have the k contains our log Calabi Yau v, and it has a natural compactification given by the projective bundle associated to k direct sum O. And similarly, for any for any small birational modification k alpha, we have k alpha again contains our log Calabi Yau. This part doesn't move, doesn't get modified, and it has some compactification p alpha. So we can show that consider the multiplication rule for the mirror algebra a p alpha associated to this compactification p alpha of v. Then for any p1 to pn, any points inside gamma z, recall gamma is a subset of the essential skeleton of v. And any q inside the essential skeleton of v, and any curve class gamma in the cone of curves of p alpha, such that we get a non-zero structure constant then this Q must also lie in gamma. And this curve class must lie in the cone of curves of this non-proper part, K alpha. So this says that if we denote by RK alpha the monoid ring over this cone of curves, the proposition implies consequently that the free RK alpha submodule of AP alpha with basis theta P, P inside the subset gamma is an RK alpha subalgebra, which we denote by AK alpha. And furthermore, we observe that the mirror algebra AK also has a natural grading given by tropicalization of some function. And then one can show that if we take the proj of the mirror algebra of the algebra AK, this gives a compactification of the affine mirror, of the affine mirror variety. So by considering mirror algebra for K, we obtain a compactification of the mirror family. And next, we want to extend the compactified family over this bigger toric base. For this, we need to rephrase the mirror algebra using the universal torsor. So the idea is that because the mirror algebra depends essentially only on the log Calabi Yau, and the different compactifications only modify curve classes. So the extension of this compactified family over a bigger toric base is essentially a question about curve classes of the disks, holomorphic disks contributing to the structure constants viewed in different model K alpha. So it's essentially a question of understanding curve classes, and for this, we rephrase them via the universal torsor. So since we don't have much time, let me just explain the rough idea. By considering the universal torsor, we can obtain an isomorphism of rings between the extension of our mirror algebra for K alpha to Zm, M the dual of the Picard lattice, with some subalgebra A of the mirror algebra associated to this universal torsor T, and where we forget all curve classes. So the theorem says that by considering the mirror algebra associated to the universal torsor and forgetting all curve classes, we can actually recover all curve classes of the mirror algebra associated to K alpha. And this helps us in step 3 for extension of our compactified mirror family over the moving part of the secondary fan. So the idea is to use this reinterpretation of curve classes via the universal torsor, and then we show that for different model, for different birational modification, if they have, for different birational modification, we can just compare the associated mirror algebras inside this mirror algebra for the universal torsor. And by this comparison, it gives us a way to glue all the proj of all different mirror algebras in the same way as we glue toric open affine subsets of the base toric variety. So the last step for extending to the full secondary fan is to extend to the bogus cones. For this, we have to use the equivariant boundary torus action from the Frobenius structure conjecture. There is some difficulties involved because actually the mirror family does not really extend over this toric variety because of some stacky issues. And the solution is to construct a Deligne-Mumford stack, curly TV, denoted by curly TV, associated to the secondary fan with coarse moduli space, the toric variety, associated to the secondary fan. And we extend our mirror family over this stack via the equivariant boundary torus action. So to conclude, the steps 1 to 4 together gives us a compactification and extension of the mirror family of the toric variety associated to the secondary fan. And finally, now it gives a better understanding of the two theorems I mentioned in the beginning. We have the first theorem describing the singularities of the extended compactified and extended family. And in dimension 2, we have a much detailed control over the singularities, and we show that actually we obtain a family of polarized Calabi Yau pairs. And the map to this space of stable pairs is a finite map. So that's this. It gives us the proof of this conjecture about the shape of these parts of the moduli space of stable pairs, which is not at all evident from birational geometry. Yeah, let me stop here, and thank you very much for your attention.
Thank you very much for excellent lectures.
Thank you again for the invitation. So probably because my talk involves many different mathematical objects, probably it's difficult to understand if it's the first time you listen to all these new mathematical constructions. But since I have shared the notes with you, maybe you can take a look later if you become interested in the subject.
Yeah, sure. It's always very good when a lot of different things are involved.